Yeah.
Okay, welcome to the Monday seminar. It is my pleasure to introduce Raphael Affinito, who's going to talk today. This seminar has been going on for quite a while, as many of you know. I suppose there's a lot of familiar faces here. It's Our normal mode of operation is to ask people to mute themselves, but also to encourage you to interrupt. Just go ahead and unmute and interrupt with points of clarification because it usually works out quite well to have minor points of clarification along the way. And then we'll have time for questions and things like that at the end. We have up to half an hour or so if Raphael decides to talk for an hour. That we kind of this 90-minute time slot works out pretty well for having a nice extended discussion and question and answer period. So, with nothing else from me, I will turn things over to Raphael.
Okay. Thank you, Chris, for the introduction, and thank you everybody for coming. It's been nice. I just want to say before we get started, for the last, I think, 5 years this has been running, maybe longer. That's pretty much the duration of my PhD. So it was fun to kind of chime in over the years, watch the recorded videos as things to almost study off of, and I'm happy to be having the opportunity to present. Now, like all good projects, this is very much a collaboration. So there's a lot of names below. But I'm just going to list them off because most of this work would have not been, or all of it would have not been feasible without their support. So Clay Wood, Samson Marty, Saiwei Chen, Huey or Konyuka, Achia, Ejasink, Peng Liang Yu, Giuseppe Volpe, David Bolton, Sri Sharan Sridharan, Kayla Kroll, Tushar Mittal, Marco Scudetti, Elizabeth, Cochran, Giles Peltzer, Derek Ellsworth, Donald Fisher, and finally Chris Marone. Thank you for inviting me. So I want to keep this kind of as an overview of some of the work that's been completed over the last couple of years. So I broke it up into some sections. And like Chris said, we'll keep it casual. So feel free to just interrupt me if, or just pause me at these sections. There'll be breaks in between them so you can ask questions as we go. We're going to start off by just some motivations, some background, and some methods. Section 2 is going to be looking at frictional stability transition with fluid pressurized fault gouge. Section 3 is going to be focusing on the influence of slip velocity on hydraulic connectivity of faults. We're going to get at something called drainage or kind of pore connectivity. Section 4 is looking closely at poral mechanics of partially drained stick slips, and I attempt to kind of scale this to the field, so I have implications for post-seismic behavior. Section 5 is in the influence of hydraulic connectivity on precursory signals to failure and laboratory earthquakes. And these last two are currently in preparation, so I'm happy to have some input and shop some ideas around when we get to that point. Let's start really broad and just think about structural heterogeneity. We can have like a simple block model of, let's just say, a strike slip fault in this case. You have some country rock with a damage zone and then a fault core in the middle. Obviously, this can be a lot more complex. The field's never simple like textbooks sometimes. So on the right, we can then scale that out, and what you see is you have multiple anastomosing layers, which are characterized as fault wear material. This is the fault core. So this fault wear material is commonly referred to as fault gouge, and I would say it's ubiquitous across active shear zones. This isn't anything new. I mean, I think I pulled this paper, and I guess it's adapted from the Chester and Logan work in the mid 80s and probably even before then from others. But I like it because they've made the host rock on the outside, they've taken care of it. So it's now gone. They've removed it. And then you have this architecture in the middle and they show this anisotropy of the permeability. They have K-min, K-max annotated on it. And then on the right, they have a whole list of factors. And I would say that I don't know if we really know that well yet how all those factors control fault dynamics. So I think there's plenty of fun questions to explore. And where I want to really focus on looking at fluids and then permeability. Going back to this field observation, here's an example from the Carbon-Aris work from Dan Faulkner, from Dan Faulkner studies. And there's a kind of an open-ended question, which is that if gouge is observed in fault zones, how do these fluid pathways, if gouges or localized regions, influence the mode of slip? There's another paper that kind of came to mind when I was putting this together, and that's more recent from Christy Rowe and Heather Savage, looking at localization and delocalization. So here they just have an outcrop in figure C, and then panel D to looking at different instances of localization and instances of slip. If you move to kind of maybe the mesoscale We could think about like these underground labs. This is the Bedretto Mine. This is taken from Giuseppe Volpe's work in 2023. And in panel A, they have in the mine an observed uh, slip profile, and then in D, and then looking at a rock taken in B, you can then do a thin section, which is panel C, and you see that where the D box is, you have localization control. And so this is once again, we're kind of reiterating this localization, delocalization observation. And fluids are often invoked. In fact, in Bedretto, I think they have been injecting fluids to induce slip. So there's still a lot of open-ended questions about how the fluids mediate the fault dynamics. We can get a little more specific and think about the effective stress principle. So there's Hubert and Ruby, 1955. It's very simple, where your fluid pressure will drop your sigma prime, and then that's going to directly affect the shear stress or tau on your fault interface. There could also be hydraulic conductivity. This is the ability for fluids to move and how effectively they will change the stress state on the interface. Then we'll clump a lot of other things in three and call this fluid rock interactions. You can think about mineral kinetics or kind of fluid mediated processes as a driver for changes in the rheology of the interface. We're going to focus on one and two today. This is probably the easiest for me to target in the lab. I do want to highlight that we recently had a paper come out that was focused more on three, trying to relate fluid driven kinetics to frictional stability. So I'm first and foremost an experimentalist. So I just want to do a little bit of background on the biax. One thing you'll notice with the biax is it's well worn, I would say, in the photo. You know, it's a loved machine, but it works really well. And because of that, it kind of holds near and dear to my heart. But what you're seeing is you have a horizontal piston, and then you have a vertical piston. And if you were to zoom in on, take this door off, which is this steel box right in the middle, this is what it looks like on the inside. So this kind of tan colored latex thing is my sample, and your normal stress is applied horizontally, your shear stress is vertical. And then I had horizontal and vertical displacement sensors inside on my fault, measuring essentially the near field displacement responses during any of the measurements I was making. And if I was to equate the biax to anything, I would make it like a 90 series Toyota Tacoma because it needs a little bit of maintenance, but it's gonna run forever. So I look forward to 6,000 more tests on the biax, Chris, at some point. Zooming in a little bit more on the double direct shear configuration, it's composed of three steel blocks, which you're seeing kind of lined up here on the table, and then these white layers between them are my gouge. When I jacket it all, it looks like this. So now you wrapped it in these custom dipped latex membranes. The whole point of this is to separate the confining medium from the pore fluid because you don't want to have that mixing. And then this long, tall series on top of it is my loading column. This is what I'll refer to as springs. This is one of the difficulties with this initially was just producing these stick slips because it's like an optimization problem. We don't have a lot of space, and you got to reduce the stiffness, but you don't want to, but you can't be too high in stress, otherwise things will deform. So that was why we came up with this solution. If you're to open these blocks when you're done and then peel them and look at them face on, this is what you see where the shear direction has been pulled down. And you notice there's these kind of like striations in the gouge. It's almost like little faults cutting through. If I was to just take some of this and do a thin section, this is what a laboratory simulated fault zone will look like. These serrated shapes on the top of the image are the teeth, which grip the gouge. The shear direction was like this, and then we can have an upstream and a downstream fluid pressure across this fault. So you can be flowing perpendicular to the shear direction in this case. And if we zoom in on one of these sections, you end up with something that looks like this. And I show this because, often you get people who say, "Oh, you're in the lab shearing powder. Why does the scale matter?" But I think looking kind of back at where we started earlier in this talk, we had some field observations. I would say that, if the summation of microphysical processes are probably what dictate the macro scale observations, then I think the laboratory scale is valuable. And you're seeing here like low and high strain domain and evidence of localization. So with that, we'll get into section two, which is looking at frictional stability transition and fluid pressurized faults. This was this is earlier work. This is from the start of my PhD, and I think for all these sections, I'll kind of have like a question, and then I'll have a more specific question. My very first question was pretty simple. I think it was just, can I produce stick slips in the vessel? And then we could make that more specific and say, is fluid pressure under drain boundary conditions, or does it influence the stability of quartz gouge as predicted by rate and state friction? I'll go into a little bit of background for rate and state, and I'll try to keep this brief. But so rate and state friction is an empirical framework. You have some mu initial on the right here at some given velocity, and then you will essentially do a stepwise increase in the loading velocity, and you'll have some mu final. This will evolve over some, it'll have a direct response, which is in green. This is called the direct effect, and then some evolutionary response, which will occur over a critical slip distance, d sub c. If this is negative, the difference between the green and the blue, or A and B, that's called velocity weakening. And velocity weakening is unstable. This is one of the prerequisites for unstable slip in the classical rate and state framework. You notice that there's this theta term. I've only shown two, there's multiple laws besides this, but we'll just focus on aging and slip today to keep things simple. What is state? Maybe at its simplest, we could say that if you had two grains sliding past each other, and you were to take a cross section A to A prime and look at the surface of this contact itself, as it moves past each other with time subsequently, you have some evolution of theta. It can be thought of the quantity or the quality of asperities or contacts. A nice way to think about aging and the aging law on top is that if it's not sliding, if velocity is zero, you just end up with one. So it just kind of ticks up over time. Now, to take the rate and state framework and make it a frictional stability and make it useful for frictional stability, we have to couple it with the spring slider model. So on top, we have a classic spring slider, like what you would have, if everyone's played with the slinky or maybe like a high school or college physics class, where you have some normal load, frictional resistance, and then a spring which is pulling at some velocity. You can make that slightly more complicated and use a double direct shear, like on the right, um, where the loading stiffness is K. Your critical stiffness, K sub C, has these two empirical parameters, A, B, D sub C, and then fluid pressure, which is reducing sigma. Stability criterion is defined as kappa, which is the ratio of K to K sub C. And if kappa is positive, it's conditionally stable. And if kappa is negative, it's conditionally unstable. And you'll notice two things here. One is that fluid pressure is dropping K sub C. So there's a bit of an issue where if we're invoking elevated fluid pressures in the subsurface, elevated fluid pressures in assuming stiffness isn't changing would actually create aseismic slip or creep. And over years of running direct shear tests, I can confirm that when you do have high fluid pressures, it does just creep. So that's something that we need to figure out from a modeling side. And then the other side of this is it's conditionally stable and conditionally unstable. So the perturbation size matters. Essentially, how hard you kick your fault out of stability can push it into an unstable regime. The earthquake cycle, things can be simple, and this is a simple case. We'll start here, where you have an interseismic period. On top, we're showing shear stress as a function of low point displacement, and on the bottom plot, we're showing fault slip velocity as a function of time. So you have an interseismic, which is this loading, a coseismic, which are these gray bounded regimes. We can have some background loading rate, which in this case was, I think, about 9 or 8 microns a second. Below that is a slip deficit. Above that, the fault is slipping, and it fits fairly well with the inter and coseismic definitions. We can then measure the stiffness for each of these events, and that'll give us a K, which we can kind of pipeline into our stability criterion measurements. And I do want to say that, this is a very idealized case. This is very periodic, but similarly in the lab, a lot of times we can get this tuned to produce unstable or non-periodic or quasi-dynamic events. And I'll show you what that looks like. So depending on where you were in this phase space, on the right, where you have K over K sub C, one is about the transition. So I could do something where I'm kind of moving across this regime and you get something going from stable to unstable. and it grows and eventually reaches some limit cycle. Alternatively, I could put the sample in a very quasi-dynamic regime, maybe like stick it just below 1 and leave it there. You'll get something like this. And you can produce hundreds of these. And this is very complicated to predict. And because of that, I think it's very exciting to think about the dynamics and how they evolve. Looking at a kind of traditional experiment for this approach, we have friction as a function of shear strain in this case. We load up the sample, and you'll notice at about 2 and I guess 3, or maybe, yeah, 2 and 3, I guess it's shear strain corresponding to 2 and 4-ish. We have these unload reload cycles. The point of this is that we've known for decades that the memory of rocks or the history of something is very important for controlling the dynamics at later stages. Essentially, the rocks remember what happened to them. So this means that by me doing these unload reload cycles where I move the piston down and up before I start, I'm conditioning the fault to be similar each experiment. So if I make my sample slightly different one day, this unload reload cycle will mean that the long-term endpoint is going to at least be similar across tests. So it's a good way to get reproducibility for all of our experiments. If we zoom in on this kind of shaded box on top, you see something like this, where we have a insert for friction as a function of load point in B. This is showing the stability transition. And then for C, we have shear stress as a function of time. You have the inter and coseismic stages for the stick slips. These are slow events, or slow slips, we would call them. And in the red, you have your slip velocity. For each of these, I can look at the linear elastic section of the load up and define a K, a stiffness. All these experiments were run at different effective stresses. There's about 20 of them, I think, that were successful in this case, from 15 to 20 MPa, and fluid pressures from 1 to 5. So these are fairly low fluid pressures. Um, and what you end up with is a plot like this. It's a little bit busy, so I'll explain as best I can. On the top plot in panel A, you have all of your stiffness measurements. The triangles are from unload reload cycles. So these are independent measurements of the loading stiffness just of the frame as a function of shear strain. The circles are from stick slip events. So these are measurements of the loading stiffness. And then the red line is the kind of empirical framework for K sub C. And if you then look at the ratio, so this is the bottom plot in panel B, you end up with something where K sub C of 1 is about the transition, and above which you typically have slow events, and below which you usually have fast events, with the warmer colors being faster events up to about a millimeter a second. So what this is showing is that even at low fluid pressures or drain conditions, this empirical kind of framework is successful in predicting the stability transition. And I think this means that when there's when the fault is rather drained, and we'll get into this in a little bit, it's really just the inherent material properties of the fault which are controlling the stability transition the, of the system. So the conclusion for this is that the stability transition is valid for fully drained quartz gouge across low fluid pressures. And I will emphasize that these are low fluid pressures, but it suggests that rate and state friction parameters are inherent to materials. The implications, I would say, is that in order for fluids to have a significant impact on the stability transition, there must be either a change in the drainage state or the material properties throughout the seismic cycle. So this could either be getting at that 3, which is a fluid rock interactions when we started, or the 2, which was the hydraulic properties. And this will be where we'll focus for the most of the rest of the talk. So for section 3, where I got to after that work was that we need to look at how slip might be related to hydraulic conductivity. So this is going to be focused on what is the rate dependence of fault drainage and gouge, and how does it change frictional strength and stability? The specific question could be that under partially drained fault conditions, how well does the rate and state friction model capture the frictional response of fault gouge or fault wear material? We could start kind of simply and think about almost like a microphysical model for fluid pathways. You have some wall rock and some fault core. I would say that they have 2 different permeabilities. So we have a K1 and a K2. When you're sliding, fluids can move, and you could have instances where if dilation outpaces the fluid volume or the fluid mobility, fluid pressure will drop. And conversely, if you have poor collapse or shear and the fluid cannot leave, then fluid pressure will go up. So it's the very classic poroelastic response. To model this, we had to adapt the vessel slightly. So I have a upstream and a downstream fluid reservoir. The upstream side had a constant flow rate measurement. So this is a constant pressure boundary condition. And then had a lock valve moving from left to right here. On the inside my lock valve was my pressure sensor, my pressure gauge, which I am controlling off of. And this goes with as little dead volume as possible. Dead volume refers to the volume which is not in the fault to the fault. My fault, I cannot, unfortunately, measure pressure directly in. It'd be nice if I could, but that's more of a technical challenge than anything else. And on the downstream side, I had a very, very small fluid reservoir, which was a passive boundary. And this allowed me to have better resolution on the change in pressure across the fault due to either compaction or dilation. And when these lock valves are placed, it means that I can have two different boundary conditions. I can either have a constant pressure boundary condition, where the upstream is maintaining and the downstream is listening, or I could have a constant volume boundary condition, where I close that valve and the fault is isolated. And it can essentially, it's hydraulically isolated, so it can just move as it will and change pressure depending on how pore volume evolves. And the really important thing here is that the limiting hydraulic length or limiting permeability is the fault. It's orders of magnitude lower than anything around it. So let's think slightly about, I'll kind of introduce drainage states and how it might be related to frictional behavior or even just shear stress before we get into friction. Traditionally, what I've shown you so far is what I would characterize as drained fault behavior. So over that velocity step, from V naught to V1 here at the top, you have your step function. Porosity evolves. The evolution of porosity, that the distance it takes to get to steady state at V1 is about the same distance as d sub c. Oops. And people have related it to the state term, like in the CNS model, for instance. And fluid pressure does not change. So there's no evolution in effective normal stress. And then your shear stress evolution is exactly as what's predicted in the classical models. Partially drained behavior means that your fluid pressure is seeing some change during this step. So there's instances of essentially uh, poor connectivity between the pore volume and the system outside. So it can overpressurize or underpressurize. So when you do your velocity step, it might rapidly drop as the fault dilates, but it's going to get back to steady state. It's going to go back to equilibrium. Likewise, when you step down, it might overcompact, but then it'll very rapidly diffuse and go back to where it needs to be. And then finally, you have undrained behavior, where for the same thing, essentially the fault will continue to dilate and the fluid pressure will continue to drop. And this will directly affect the shear stress that the fault is seeing. So these are kind of three end members. In reality, it's a spectrum. And I think that the partially drained behavior is probably evolving as a function of strain, normal stress, and slip velocity. So what we're going to do is try to constrain this partially drained thing, this partially drained zone in the middle. To do that, we need to think a little bit about porosity and coupling porosity into rate and state friction. This gets at the dilatancy factor, or epsilon, shown here, which can be related to the change in porosity, where you have your V naught, your theta, and d sub c. At steady state, you can say theta is equal to V over d sub c, and then you can define your steady state porosity as epsilon, and then essentially the size of your velocity change, ln V over V naught. Assuming the changes in fault thickness arise from changes in pore space rather than like plastic deformation or solid deformation of the skeleton, then you could rewrite it as a change in H over H, where H is your thickness. So H is the width of the fault zone. So as the fault is opening and closing, we can say that all of that is all of that kind of clapping and opening is occurring from changes in the pore volume. We can then take one of the functions and say that, okay, we'll look at the evolution of friction with time. You have in the first term, you have your springs, you have your elastic coupling, where VLP is the load point. And then on the end, you have friction over your effective stress. And then what you have is the evolution of fluid pressure with time. The evolution of fluid pressure with time is going to be a function of three different terms. So you have your elastic or recoverable changes, you have your inelastic or plastic, we call them permanent changes to the fault zone, and then you have your drainage term, which is going to be capturing the changes in the hydraulic properties of the fault as you shear. Um, During these tests, there was a series of about, I think it was 24 experiments, and I'll show three here, which capture kind of the general stress range. But we would load in each experiment under fully drained conditions. This is shear stress as a function of load point. The light blue is the highest effective normal stress, the lowest pore pressure. The dark blue, or kind of, I guess it's like the light green kind of color. The dark blue is the lowest effective normal stress or highest fluid pressure. So it goes from about a lambda, like a fluid ratio factor of about zero point 0.3 up to zero point 0.6 in this case. And after we loaded in the sample fully drained, then on this first dashed line, we would have the constant volume boundary condition tests where I would do subsequent step ups and step downs in the loading rate. So velocity steps. And you would go like it's shown in inset B, you from 3 to 10, back to 3, 30, back to 3, 100, and 300. Each time going back to 3. I would repeat this twice. And then I would flip to the next boundary condition and do constant fluid pressure boundary condition. So you would essentially change between forcing the fault to be hydraulically isolated and allowed to have some recharge, but the recharge is dictated purely by the diffusion across the fault length. And then I flipped it, so I know I could correct for for any strain effects which occurred. What you end up with is some measurements which will have, well, I'll start from the raw measurements in panel A. So delta H is your fault thickness, which we convert into dilation. The long-term trend of this is going to be a decrease because the fault is thinning. So you're losing material as you shear. So I have to detrend this, but it's detrending in a linear fashion. So by detrending it, the black line, you essentially extract the short-term changes, which we can relate to dilation compaction. And then in gray is the delta H equivalent. This is the fluid volume, which we take from the intensifiers, the fluid volume which is displaced, and we convert that volume, which is displaced, into a equivalent displacement using essentially assuming that the fluid is filling the pore spaces. And what you'll see is that it does not need to be detrended because you're not losing any fluid. It's just moving into the fault as to maintain the constant pressure. And on panel B, you have shear stress on the top. So this is a 3 to 100 velocity step. And then you have your detrended signals for the layer thickness and the equivalent dilation, which is converted on the black and the gray respectively. What I've noted is an initial and a final with the subscripts. So for delta HI, this is I put initial as when I kind of reach the steady state porosity in the black. And the important thing to track here is that the steady state porosity, which you're reaching for the dilation response, the equivalent fluid response, which is the green or the green dot below it, is not caught up. So they're not fully in communication. So what this shows is that a really small perturbation in shear stress can induce locally undrained fault conditions. And this is important because this slip velocity 3 to 100 is actually it's quite a small change. When we think about seismic slip rates, you can have orders of magnitude larger differences between the background late and then the fault unlocking or even creeping. So I do not think it takes a lot of change to have a locally undrained response, which is going to directly affect the effective normal stress. And then importantly, in this case, it's the system wants to get back to equilibrium, but the duration which it takes to get back is much longer than the critical slip distance. So if someone wanted to just take, I mean, somebody could take a two-state evolution law and try to make your second state terms and critical slip distance very, very long. But we'll get to that in the next part. I think you could try to constrain that with maybe different hydraulic parameters. So as for the drainage condition, we've established that these faults are not fully drained, even for material. I should have mentioned this is like a granite. So this is what would be typically considered to be well drained. Even though it's well drained, quote unquote, it still behaves partially drained when you perturb it enough. Um, This is what this plot in panel A is showing. So on the x-axis is your mechanical dilation. On the y-axis is your fluid equivalent. A one-to-one line would be full communication between the pore volume and the fluid volume. And you can see that on the one-to-one line is your final response. So the system moves towards being drained. So the diffusion is not, or the hydraulic properties are not so slow that it never becomes drained. But the initial response at or around the length scale of the critical slip distance is that such that it is undrained, where the mechanical dilation is outpacing the fluid response. That's what the black lines are showing. In panel B, we have a series of the dilatancy coefficients returned from this study, as well as some other ones. I kind of just combed the literature. The diamonds, the gray diamonds are from John Samuelson's work. The yellow crosses are, I believe, from Isabel Ashman. She was Dan Faulkner's PhD student. She did a lot of really good tests on this as well. And then you'll notice that there's some other tests which are at higher, have very high dilatancy coefficients. And I believe these are from experiments that have very big step changes. So these are very, very large or high slip velocities. If we look at the spectrum of fault behavior, I'm just going to kind of show some raw data plotted to give you insights to how these changes are manifested. We'll look at light, or the light to the dark color corresponds to the size or the magnitude of the velocity step. So on the left is going to be blue, which is your constant fluid pressure boundary condition. And then on the right is your constant fluid volume. This is the green. And what it looks like is that locally undrained fault behavior increases with shear stress. So you'll see that, the peak is not necessarily higher, but but the steady state is higher. So it's strengthening over time. For the downstream fluid pressure response, the small inset below is showing the upstream. This is showing that our upstream is constant. So the downstream is right above it is showing these small drops during the velocity step, and then these little overpressurization kicks that occur on the downstep. So this is showing dilation, compaction, that's temporarily changing the effective stress state of the fault. And then on the right, you have the undrained response. So as soon as you start to shear slider, the fault's going to dilate, your grains are going to strengthen, you're going to get a prolonged dilational um, fault thickness evolution is delta H. Similarly, you get some steady state or weakening in the delta H response, but for the constant volume, it continues to increase for a very, very long duration afterwards. And then you can take the average of your upstream and downstream and get an effective normal stress evolution. And what you find is that these minor changes are not accounted. Uh, you could use the Linker-Dietrich alpha term, which people have used in the past, but I think there's a major gap there, which is that, to my knowledge, no one's actually measured the alpha term for just perturbations in fluid pressure. They've only done normal stress. So that's kind of an open-ended thing that needs to be fixed if people are going to use that to adapt it. We can try to model this a little bit, and I can look at the upstream and the downstream fluid reservoirs. I can treat them as a kind of volume averaged like block model. So we can assume an effective singular fault pore pressure just to make our life a little bit simpler. And then we could have three box models. We could have the upstream, the downstream, and the fluid fault reservoir. And I could define the upstream fluid pressure and the downstream fluid pressure respectively, where V is the flow rate. You then have R, which is this characteristic thickness of each reservoir. You have your compressibility terms, and then K in this case is permeability, not stiffness. Maybe I should define that differently. But then you have your dynamic viscosity, the length scale, and your pressure gradient. You'll notice that for each of these, there's P internal, and P internal is what I do not know. I cannot measure the internal pore pressure. So to kind of get around this a little bit, I can play a little game where I can say, we know the downstream fluid pressure response in this small isolated reservoir. And what I'm showing here in panel A before I continue is the fluid pressure response as a function of time over velocity step. So blue is the upstream, red is the downstream. And by saying we know the downstream fluid pressure, the internal fluid pressure has to be lower than the downstream because it's pushing that gradient, it's driving that gradient across the fault. We're just observing in this dead volume on the other end. So then we can solve the equations before and change the permeability, which would give us the essentially make this logic true. And this returns an upper limit for an effective permeability. This is not a real permeability. This is an effective permeability because it's over that R term for the fault during shear. And where we end up with is about 5e to the negative 19. So the effective permeability for the fault. And it's not entirely far off of static permeability measurements for gouge in this configuration. Static permeability measurements range from about typically around 18 to 19. So we're in the same ballpark, which is nice. In order to kind of check whether the logic worked, we can then work in the opposite direction and say, okay, with this permeability, can we return the flow rates which we get out of our pump on the upstream? And if we make the downstream and the upstream permeabilities the same, and say the average system is exactly the same across the fault, this is what you end up with, where if the black line is the data, the model, which is the orange line, is not converging at all. But if you make there be a contrast and say that one side of the fault, in this case, I believe it's the upstream side, which is the side that's being actively sheared as well, is less than the other side of the fault, you end up with the data converging and agreeing more with what we observe. And the contrast which we found was needed was at least 4 orders of magnitude. And this is effective permeability, so almost like K over L. This is not actual permeability K. So you could reach this by decreasing K or changing a length scale. It could be a hydraulic length scale. And I don't think this is entirely too far flung because if we just think about initially when we talked about heterogeneity in structures, the type of microstructures we're producing are something like this. So there's clearly lots of structural anisotropy which are being accumulated in the fault zone as we shear. And kind of in conclusion, minor changes in shear rate have a primary effect on the fault zone drainage. And when I was rereading John Samuelson's work when I was putting this together, and I realized that he has this little paragraph. You know, when you find someone who kind of did what you want to do, but they did it like 10 years ago. So Samuelson, although he never showed it, he has this little quote, and he talks about it a bit in his discussion, where he says physical dilation exceeds fluid dilation at the upper end for the highest velocity step sizes, which may indicate dilational hardening and or non-interconnected pore space. So he never reports it in his paper, but he talks about it a little bit in length, which is nice. So this is in broad agreement with other studies who have tried to constrain these rate dependent changes in drainage condition. So in conclusion, I would say that for fault zone materials, which are typically assumed to be well drained, so this is indicative of you could think of like upper crustal conditions, unconsolidated material, even things which we typically think are relatively permeable. I would say that small perturbations in loading rate or slip can induce locally undrained fault conditions. And then it becomes a question of really how long those hydraulic length scales are and whether or not AKA can affect things in terms of the long-term dynamics of the fault zone. The implication is that the existing rate and state friction framework in the purely classical sense is not sufficient to model the full response of the drain system. We talk about it a little bit more in the paper. So what we put forward was rather than using multiple state terms to get at these different hydraulic length scales, you could try to use two effective permeability terms. Because in the lab, if you have the ability to measure these hydraulic properties, then you could use the classic rate and state paired with the pore mechanical framework from Siegel and Rice or John Samuelson or this approach here and get at the same response. So in section 4, now after I kind of was able to produce stick slips and then was able to look at how loading rate might modulate the drainage state of the fault, you'll notice that in the previous paper, we were doing velocity steps that were about 100 to 300 microns a second. And this is on the order of when we have slow slip events in the lab or slow stick slips. So then I wanted to try to produce stick slips under these partially drained conditions and see if we can pull out some observations. And I wanted to jump and see if I can try to relate this to field scale observation. So at the end here, I try to kind of scale up a little bit and do my best to see if we can go from the lab to the field. Specific question could be that if slip velocity and localization related to the hydraulic properties of gouge, you can say fault zones, does this impact the dynamics of stick slip events? I do want to note that in terms of poromechanical responses, I'm not the first. There was a really good work by Marco Scudetti in 2015. He used single direct shear on glass beads. So the benefit, I guess, that I have over that is that in my study, I'm not fully drained. His responses were fully drained. He did a really nice study systematically showing how the boundary conditions, loading rate, and effective normal stress influence the poromechanical response. And then more recently, there's also the work from Proctor from the USGS group in quartz gouge in the triax configuration. And similarly, there's also Nicola Brantu's work, as well as with Franz Abben. Um, Advantageous, I mean, even though they have the really, really unique fluid pressure sensors, the nice thing about the direct shear configurations over the triax tests is that we can accumulate more shear strain and more stick slips. So lets us get kind of at these the long-term history effects if they're relevant. Overview of these tests. In A, there's a little, Raphael's conceptual model of, I guess, of a fault here. And we could zoom in on this principal slipping zone, which is, we have C. And in C on the bottom, we then could define what we talked about previously, where you have a thickness H. And I'm going to say some hydraulic length scale, which we're going to call H star. And I'm flowing across the fault from upstream to downstream. On the right, we have some example stick slips from this experiment P649, P6049. We have the post, inter, pre, and co-seismic stage listed for each, and the top is shear stress with the elastic loading stiffness denoted for each stick slip event. On the bottom, sorry, below that in red, we have the slip velocity from the internal measurement and with the background loading rate. So you're seeing the slip deficit and then acceleration. Below that, there's porosity, which is taken directly from this thickness measurement. So you have dilation and compaction occurring as the events are continuing. And then below that, we have fluid pressure. So the dark blue is your downstream fluid pressure. The light blue is your upstream fluid pressure. Upstream is not changing, is maintaining. And then downstream is overcompacting and pressurizing on the coseismic, going back towards steady state on the interseismic, and then dropping pre and dropping more coseismically. At the inflection point, when the fault starts to decelerate, it jumps back up at the end of the coseismic. And we'll get more into the dynamics in a little bit. These experiments take place at higher stresses than the first set you would have seen. We have much better resolution of the porosity and the fluid pressure in this case. So we're at fluid pressures over 20 MPa and normal stresses, effective normal stresses ranging from 30 to 40 MPa. And once again, they were done on the vessel at Penn State. So we've gone over the classical rate and state stability limit. This is what I would call the drained response. I'm gonna kind of walk through, I guess, well, not walk through, I'm just gonna show the end members from the Siegel and Rice formulation and the 95 formulation. A little bit adapted though in this 2025 paper by May. He did a good job kind of non-dimensionalizing it. You have a second term, which we can call the dilatancy hardening factor, E, and you'll see that in this E term, you have the bulk compressibility and epsilon. So all this previous work is great because we've defined epsilon at these relevant velocity changes. So we have everything we need in this function. 3 is hydraulic diffusivity. This is where C comes from. And you have C as a function of K over your viscosity and the compressibility. Your compressibility is the porosity of the fluid and the pore compressibility over the material. You then have your drainage function, which takes this. It evolves with C d sub C over V naught and then L squared. And what you end up with is kind of limits where if it's much greater than 1, diffusion is fast, the layer drains during slip, and this is the drain limit. And then if it's less than 1, diffusion is slower, and the layer locks up and strengthens. So you end up with a final poromechanical stability, which is K sub C is a function of K, the classical version, drained, and then you have 1 minus FE. Um, so if one of these drops out, then you should end up with K sub C drained, which is nice. That's the two physical limits. So you could have F going to 0, the drained limit, and you end up with the classical response, which is great. That's kind of what we'd expect. And then if F goes towards 1, then you get this undrained response where the dilatancy factors are dominating. We can define a critical hydraulic length scale H star by setting slip and diffusion timescales equal. And you end up with H star is the root of CD sub C over V naught. Physically, H is a thickness below which the actively slipping zone can fully drain during a slip event, and above which it cannot. So if your fault thickness is less than your local than your critical hydraulic length scale, then it's drained and instability is possible. But if your fault thickness is much greater, then you could have instances where it's locally drained and dilatancy starts to win. That's kind of the fundamental logic. To test this, we did a series of tests where here in panel A, this is an overview of another experiment where we have friction as a function of low point displacement. And zoomed in, you'll see this inset stability transition corresponding to low point displacements at about 14, where you have shear stress becoming more unstable as a function of strain, and then below that, subvelocity, porosity, and your delta of fluid pressure, the difference between upstream and downstream. What I would like to note is just that you'll see that when it transitions, there's this kind of modulation in the amplitude. And this is it's kind of cool when you get these stability transition just to the right regime, you can get these long period modulations, which are difficult to explain, but are always kind of exciting to see, I think. And that shows up really well in the slip velocity and the dilation data. You can see it moving. Now, if we take all the stiffnesses from these stick slip cycles, these K values, we can plot in panel B, the elastic loading stiffness on the Y as a function of the shear strain on the X. And you'll see going from blue to green, this is slow to fast. But fast in this case is only 100 microns a second. These are very slow events. These are very small, slow slip events on the gouge in the vessel. And I did that purposefully because I want to be in that regime where I know the parameters for the functions I need as we defined in the previous section. And what's interesting is that if you take this case of C from the previous slide and put in an H star or a critical length scale for 3 and 30, you end up with these envelopes that are plotted as the dashed lines. And the stick slips only appear when K sub C passes the 30 microns length scale. So what this tells me is that somewhere between 3 and 30, if the theory is correct, is this critical length, which is controlling, or this critical hydraulic length, which is controlling the dynamics of the stick slips. And this is actually okay because, like images we saw prior for the shear zones I showed, you do have like very localized regimes which are controlling the dynamics. If you look at a poor mechanical like feedback for the stick slips, you have something like this, and now I'm plotting all of the dynamics as a function of the on-fault slip displacement. So rather than looking at the far field measurement, you're looking at directly the actual fault motion. That's why it looks a little bit stretched. Usually we don't show things in terms of the on-fault, the far field. So you'll see we have the post, the inter, the pre, and the co for 1, 2, 3, and 4 noted at the top, and this is repeated for each. Um, for the slip velocity, we have the background loading rate once again. These are very slow events. For the delta H, this is the change in thickness. It typically is dilating slowly during the interseismic and then dilates for the first part of the coseismic, but as the fault starts to decelerate, it compacts. It compacts rapidly. In the fluid pressure, the fault is dropping as the fluid pressure is dropping as the fault dilates, and then as the fault rapidly compacts, the fluid pressure jumps up and increases. Importantly, there's a phase lag. It it if the system was purely in communication, you would expect that as the fault compacts, the maximum compaction would be correlated to the maximum drop in fluid pressure. But what I see is that, in fact, the fault continues to compact quite a bit after the fluid pressure has reached its maximum overpressurization. So this means that there's some sort of miscommunication that's occurring within the fault zone. Panel B is getting at kind of the I guess broad polar mechanical dynamics where you have where the Y is your mechanical dilation and the X is your downstream fluid pressure. So starting at the right side in one, kind of right below the zero on the color bar, you move over, and the color of this is the fault slip velocity, and then the interseismic is this kind of nearly linear section where as the fluid pressure is dropping, the fault is dilating. The pre-seismic is this tail right before it rapidly turns and then slips. But most importantly for us was this phase leg, and we thought that if there's a phase leg, it means that the simple poroelastic model is not sufficient because it means that there's something that's not in communication. And this gets at where we'll try to go on the next stage. So this is one of those questions that like every lab person kind of dreads. You give a talk, and then someone at the end is like, "Oh, how do I use this in the field?" So I try to beat people to it today. So I was working with Giles Piltzer and Elizabeth Cochran, as well as Tushar Mittal, and we were thinking about post-seismic responses, which pre-seismic's exciting because it's we can use it to forecast things but post-seismic's nice because we have a lot of data and we have different types of observations as well. And maybe a little bit longer. So there's more to test, I would say, in the short term. This is rapidly changing, but where I'm looking here, I think this is the Landers earthquake, I believe. And there's a comparison of different responses in the ground motion. So to take out of this is that the poroelastic response is the dotted line. It doesn't do very well if the ground truth are the dots. But when you have purely after slip, this is the dash line. It does a pretty good job, but the after slip with the kind of like rebound seems to be the best for tracking the data. This is kind of evidence for poroelastic coupled with something. And there's kind of a question mark there on whether or not we're going to use it. And this isn't only for earthquakes. I mean, this is only for the landers. A good example is also the BAM earthquake, where they look at dilatancy recovery in Iran. There's also this recent work from Greg Barroza, who was looking at kind of pore fluid aftershock triggering for the landers sequence. And then even just looking at landslides, there's some work by Noah Finnegan and Damien Safer. So there's quite a bit of data out there, and there's probably more that I'm not aware of, but these are just a couple that came to mind for why this matters. So what we're taking here is this is the 1999 Hector mine earthquake, magnitude 7.1. We have the post-seismic surface deformation, which were measured. So this is INSAR data. So it was 11 passes using two different satellites. On the left, we have it just the image, and then on the right, there's the LiDAR response. If we zoom in on just this section, Gallus picked some spots. So we have spots 1 through to 6. And then for each of these spots, we can look at how the subsidence after the event is evolving. So we have subsidence from 1 to 6. You'll notice that there's quite a spread in the degree of subsidence, and I believe this has to do with there is a large lacustrine deposit moving north, or sorry, moving south. No, it's north. So we think that maybe the changes in geology are influencing the actual ground response as you have different kind of like elastic properties in the different lithologies. But what we can do is in the lab, we can try to kind of non-dimensionalize the problem using this critical length scale. So in my lab fault, I have my steel forcing blocks. The total fault thickness is about 2.5 millimeters. But we saw in that prior plot that my H star might be somewhere between 3 and 30 microns if the theory is right. And we'll go on a limb and say that we're trusting it for now. So we'll say about 30-ish microns. I can then, using all the parameters, calculate hydraulic diffusivity. I get about 10 to the negative 8. I'm measuring my fault perpendicular dilation, and then I can calculate a characteristic time scale. We'll call that T care. It just has H star squared over C in seconds. And then conversely, we can do this for the Hector mine response, but it's a little bit tricky. We have to make some assumptions. So for the Hector mine response, we'll say Um, Previous work has mapped it out to be about 100 meters wide, but 100 meters is probably not the localized region or the region that's actually like the principal slipping zones. So we'll be pretty generous and we'll take the same ratio that we use for our faults. Or sorry, we'll use a range of about 3 to 30 meters or somewhere in there. And we can calculate diffusivities, which are about 10 to the negative 5. This is quite a bit lower, usually at 10 to the 2 for field studies, but we have to go a bit higher or a bit lower, sorry, because um, we need to get the response time to match. Because what we find is that if the response was purely poroelastic, it would be very, very rapid. So we're thinking that if the zone is localized, then there's a possibility that the diffusivity is actually smaller than the kind of typically reported higher diffusivities for field studies. But there's another issue, which is that the strain in this case is vertical subsidence. So we need to convert the vertical subsidence into which we use in the bottom. So we use this isotropic collapse. So we're assuming vertical strain from volumetric compaction, which is in the bottom. And when we do this, so we have a T characteristic of about hundreds of days in this case. So we can take our T care and we get T star based on the two responses. And what we find is something like this. So for the Hector mine response, on the left is panel A is the INSAR data, the geodetic data. Panel C in this case is the average response for subsidence for the Hector mine spots in the gray in the back, and then my post-seismic response in the fault thickness and in the green. This is for 30 events. And what you find is that it actually kind of shockingly collapsed in a really good way. So on the x-axis we have our T stars is from 0 to 1, it's normalized, and I just normalized the response on the y-axis as well. Um, and initially we were a bit surprised, but then I thought, is this realistic? And we came to the conclusion that I mean, I love this paper by Weberly and Shimamoto. They mapped all of these fault zones and they measured the permeability, right? And they just find how complicated it is. So I think it's fair to say that if these localized hydraulic length scales are what control the stress evolution, and that's directly proportional to the poroelastic response, then I don't think that this is too far-fetched. And it's important as well is that if the system was purely diffusion controlled, like or just hydraulic diffusivity, sorry, it would occur much more rapidly, like in just a couple days. And if it was some sort of viscous relaxation, it would take thousands. So there has to be something in the middle. And this is what we came up with was that you have this kind of poroelastic response, which is also mediated by a limited length scale, which is changing the stress. As well as if you were to take a classical like slip or after slip law from say like Chris's work, it fits the data, but it over predicts early and under predicts later. So this is actually a bit closer to the observed signal for the Hector mine after slip. So in conclusion, the Poor mechanical framework for frictional stability is valid for I think the kind of general dynamics, but we could try to incorporate a critical limiting hydraulic length scale, which may help control the dynamics a little bit better. And this kind of follows the theory that we showed earlier from the non-dimensionalized response of Siegel and Rice. And the implications is that local processes dictate the broad scale dynamics of fault zones. We should, well, there's a little typo there. So I think we should attempt to kind of quantify the scale in the lab a little bit more if we can, and try to scale up when possible. And obviously that post-seismic deformation observed on faults may arise from hydraulically mediated processes. So this is in agreement with what some people have put forward in their discussions in a lot of uh, INSAR or kind of remote sensing studies. For section 5, we'll look at the influence of hydraulic conductivity on precursors, signatures to fault to failure in laboratory earthquakes. So we'll start off and just, I think the broad question I started with here was that do partially draining laboratory earthquakes have different precursory changes in elastic properties prior to failure? Specifically, maybe what I was thinking was that does dilational hardening impact the emergence and duration of precursory drops in wave speed and amplitude? And we'll motivate this just by saying that um, this isn't a case from the 2009 Locklear earthquake. If you look at let's see, GPS is the gray data, but we want to focus on the DV overview, which is the black dots. You have this kind of decrease in the wave speed or the relative change in wave speed prior to the event. This is exciting because we think maybe we can try to forecast uh, when an event would happen. And there's a caveat here. Precursory signals are rarely observed. Typically, they don't exceed the background noise, but that doesn't mean they're not there. I think it's kind of it could be some path effects or other things which are unideal for certain cases. So it doesn't mean it's not worth trying to look into the physics. There's been, I guess, like decades now of laboratory observations looking at precursory changes in the elastic wave speeds. Or sorry, changes in the elastic properties of faults. I'll just show Sharon's work from 2021 of the EPSL paper. I've listed Marco and Usatinti as well down there, but there's countless others. So sorry if you're not in there as well. But what Sharon showed is that you have in black on the y-axis, you have shear stress, and then on the right y-axis in the blue, we have our stiffness or our kind of specific normal stiffness, and this is the function of time. And what he showed was that about when the fault starts to become non-linear, or when it deviates from linearity, you get this drop, this precursory drop in the stiffness. This is kind of related to how we think of contacts. So in a dry case, you could have some grains in contact. In this case, K is the contact stiffness. The contacts are aging and stiffness builds. And then when it slips, the contacts move, they're broken, and then K drops. So I believe the title of this talk might have been like uh, precursory. It was like creep and precursory changes. So this is getting at how, the motion prior to an event preceding it is what can decrease the amplitude or the quality of these contacts. I'm going to put forth that, maybe there's a competition between contact stiffness and hydraulic conductivity. In the dry case, it makes sense that K drops. But in the wet case, or when the fault's saturated and maybe let's say partially drained, like we've seen now for the last few minutes here, when your fault is at T0, the contacts are aging. They could be strengthening more rapidly due to like fluid mediated processes. But then when the fault slips, you have a competition where yes, you've lost contact stiffness, but if the fault dilates and your effective normal stress in the fault rapidly increases, then you actually have a strengthening the skeleton of that fault. So you almost have like hardening, which could mute your decrease in your elastic properties of the fault. So that's what we're going to test, and that's what I'm going to see if it's feasible. And happy to have input from everybody at any point. Overview of these tests, once again, the double direct shear configuration. But now we've embedded the blocks with two piezoelectric pairs. These have a central frequency of 500 kilohertz. So there's an S pair and a P pair, and we pulse kind of simultaneously. So this is active surveys. So you get S to S, P to P, P to S, and S to P, which is nice. Kind of an overview of the tests. Once again, it's you just get the stability transition at the same low point. Everything's kind of what we'd expect following the physics, and all the boundary conditions we had tuned. A sample of one of the waveforms. So this is the S to S reference waveform. For the reference, I believe I would stack the first 100 waveforms to give me a cleaner reference signal, and that's what this is. So we have in this blue box, what I picked is kind of the ballistic. So this is what I would refer to as the mode converted P wave from the S transducer when it hit the first interface. I don't know exactly where the S wave is coming in. I can do my best to kind of calculate, but there's a lot of interfaces in this configuration. So to be safe, I chose the S packet as this kind of large body packet, large amplitude body packet, just to be consistent across all the different picks. And then There's a bit of a gap, which may not be appropriate, but I call this the coda in this case. And the coda was defined by this kind of long-term decrease in the peaks after the waveform. So that's the red. So then we use the ballistic, the body, and the coda to calculate wave speeds, amplitudes, respectively, and compare. So looking first at the drained experiments, this would be analogous to the literature that's already out there. So like, for instance, Chiron or Marco's work. You have shear stress on the top, stability transition, and on the bottom we have our, I realize it got cut, but we have our, in brown, there is the time shift, and in yellow is the amplitude. So apologies for the amplitude being cut, but the amplitude is the yellow one. And what you'll see is that this is the raw data. So there's these long-term trends, which I think I'm not entirely sure where the long-term trends come from. I think it could be due to the gouge evolving, but it could also be due to as the central block is moving in the experiment and the side blocks are fixed, there is internal plumbing or internal, essentially, there's pipes inside of the central block. So as the central block moves, maybe the wave is picking up this change in geometry, and that's where these kind of long-term changes are arising from. And on the bottom plot, you'll see the wave speed. The green in the background is showing the fault thickness. The fault is thinning. So this is why the wave speed looks so flat, because the long-term change is just a decrease. So we need to detrend all these signals to see the dynamics of the stick slips. The dark pink is VP. The light pink is VS. This is chosen from the S to S pair, like we saw in the reference waveform prior. We can do the same thing for a partially drained experiment. So this is a test now that has, rather than being the contacts are just saturated and there's no fluid pressure, now we have elevated fluid pressures. I think it's 25 MPa at the same effective normal stress. And these are partially drained. So we're getting changes in the fluid pressure during the stick slip events. Panel B is what we'd expect, the same. Panel D, where you once again have your time shift and your amplitude in the yellow with the long-term trend on it, but nice and clear as these small-term changes. And then F, we have once again the VP and the VS and the fault thickness. You will notice that the fault thickness in F is a bit lower. This has to do with you get a lot more creep initially in the fluid pressurized tests. So you lose a little bit of material. So there is that change. And then the VP VS ratio is about 1.6 for the dry and 1.7 for the wet. When I detrend the response, you end up with the kind of cycle to cycle dynamics we would like classically think of for the stick slip cycles. So the drained or humid fluid boundary condition, this would be once again the kind of like classic published work that I think people have seen. You have shear stress on top, slip velocity this time as a log scale. These are faster events this time. Your fault thickness in green, and then your time shift. This is from the coda. In this case, the coda waveform was the coda was the cleanest, which I think makes sense. And as you know, it's bouncing around and sampling as much of the gouge over the cycles. So I went with the coda because it gave me the most consistent measurement test to test. And then on the bottom, you have the RMS amplitude. There should be an amplitude after that in the yellow. What you'll see is that the peak for the time shift and the RMS amplitude happen really early. So you get this kind of these two really long precursory drops in both of them preceding the event. And this is consistent with Chiron's model prior, because if you look at the slip velocity, the fault is kind of it's starting to accelerate at those points. It's leaving the slip deficit and starting to creep and break those disparities. So that makes sense with the basic model. But the partially drained test is slightly different. So it looks like the shear stress is the same, slip velocity is the same. Now, in terms of the dilation, you now have fluid pressure as well, where you're getting these small overpressurizations and then coseismic drops in the fluid pressure and recoveries. But now what you'll see is that the maximum for each of the time shift and the amplitude is occurring later. So these precursory durations are actually a little bit shorter. You could maybe move them around. There's some change event to event, so it's not perfect, but I would say that in terms of all of the events on average, it's quite a bit shorter than the dry or the humid cases. Now, if we take, I think this is like 87 events from the fluid pressurized case and just kind of average them and look at the range of behavior. That's what we're showing on the right. The top two panels, A and B, I'm sure you guys are all familiar with this point, so that's fine. But then panel C, we have our fluid pressure. You're getting your kind of precursory pre-seismic drop in the fluid pressure and then co-seismic overpressurization. Everything is zeroed on the onset of slip. And then we have the RMS amplitude and your time shift in D and E. And all this is really showing is that this precursory duration is actually quite short. It's only happening like about a second prior to the event, different from the dry cases you saw on the last slide, which were happening quite a bit in the interseismic. And it looks like the precursory drop for both of them is happening actually about in phase to after the drop in the fluid pressure. Um, so maybe that's helping or telling a little bit of the story and saying that these changes in affecting normal stress are maybe counteracting the response. But needless to say, there's still a precursory signature, which is recoverable in the partially drained tests. And then in panel F, we can do the dV over V, so your change in velocity or your relative change in velocity for the VP and the VS. VP is the dark pink, and the VS is the light pink. And what's interesting is that the VS changes sooner. If you squint, you can obviously see it. I didn't annotate it, but it changes sooner and it drops a little bit more. And I believe this is because our S wave sensors are vertically polarized and we're shearing the fault down. So I think maybe the S wave is picking up that like structural, that preferred orientation of the fabric. Maybe that's why it's more sensitive than just the pure ballistic going through. But open for thoughts on that one as well. So it looks like what we can say is that the duration of the precursory decrease in time shift and amplitude is much shorter than in the dry cases. So this may be evidence for competition between asperity stiffness and dilational strengthening during stick slips. And in conclusion, I think the simple answer is just yes. It appears that, or maybe I hope it's yes. I think it's kind of exciting that dilational strengthening can shorten the duration of a precursor. Implications, is that bad news? I don't think so. I think it's saying that these changes are still recoverable, and the duration of stick slips in the lab are seconds, right? So this is not entirely analogous to the field in terms of the time history. We're still seeing a drop. So the drop is the competition between the creep front and your hydraulic properties of the fault. So that does not mean that it will not appear in nature. But it could explain why some studies can't resolve, even if path effects are, say, like advantageous in certain cases. And that's it. So thank you, everybody. And I do want to thank a couple people. So I just want to thank Stephen Swavely for his support over the years, Dr. Fiore for the help on the SCM, and then Andre Niemeyer and Ernie Rudder were extremely helpful reviewers for a couple of these projects. So thank you very much. As well as Cristiano Colantini, Leone Affinito, and then Fabio Trepetta as well for their support and discussions. If any questions, I'm happy to answer. I went a lot quicker than I thought I was going to go, so that's good.
Thanks a lot, Raphael. That's a great talk. Yeah, you say you went quickly, but you did talk for over an hour, so that's good.
You serious? Oh, wow.
You don't have a clock there. Anyway, that's good for you. I'm going
No,
to
no, yeah, you're right.
I'm gonna stop the recording and I'll give people